All right, let's take a look at this question. There's something that's a little tricky in it that honestly took me a while to figure out. So I kind of want to walk you through how you're going to solve it. So first, notice here that we are going to be integrating over theta. This problem is much easier if we integrate over theta. So we're going to break this arc here up into a bunch of little ds's. We're going to pick a little delta s here. And then we're going to find the electric field from this little bit of charge right here. We're going to build a Riemann sum. So we're going to pretend that this is a point charge that's here, and that's going to create an electric field vector that points away. And that was supposed to be straight along that line there. Okay, so we know this little ith electric field from, so we've broken this up into n equal parts. We've done a partition here, and we've taken the ith one. So this might be theta I, you might look at it as. Then in magnitude, EI will be approximately K times the charge in there. Let's call that QI. That's the amount of charge that lives in that little delta S, divided by the distance squared, R squared. Now, we got to find QI, how much charge lives in there. Well, my total charge all the way around here is Q. So my charge density, let's call that lambda. That'll be the total charge Q divided by this total length. Well, my total length here will be half a circle, pi r. So that's my charge density. So how much charge lives in delta S then? Then in that little chunk delta S, the amount of charge dq will be the charge density, lambda, times delta S. This is charge per unit length. So I've got a total charge Q, and I've divided by its total length here, half a circle, instead of 2 pi r for all the way around, pi r. That's charge per unit length. I've got a total charge of Q. The charge that lives inside this little chunk right here will be that charge density times the length of that. The length of that is delta S. So that will be Q delta S over pi r. Now, again, this problem is so much easier if we integrate in terms of theta. So now I'm going to make this change. You may remember S equals R theta from your trig class. So delta S is approximately R delta theta. R doesn't change. So that gives me delta Q It's an ugly delta Q. And by delta Q, I mean the amount of charge. Let's call it QI, like we did up here. The amount of charge that lives in that little section there will be Q. I'm just rewriting this, delta S over pi R, rewriting this. But delta S is R delta theta. And the R's cancel. And we get Q delta theta over pi. So I've got some little delta theta here that is this change in angle here. And theta is this angle here from the x-axis. Now we're going to be using sines and cosines here in a second. This is where people get this problem wrong, is they'll try to call this angle inside here theta, and they'll measure from the y-axis. Sure, I could name this angle in here if I wanted to, but if I'm going to use sine or cosine, by definition, sine and cosine measure from the positive x-axis. And since we're going to be doing that in a minute, I need my theta, the guy I'm measuring, to be from here. So when you actually do this problem, your limits of integration have to be from pi over 2 to 3 pi over 2. If you're trying to measure an angle in here and say you're going from 0 to pi, then you're going to get the wrong answer. Or a lot of times we have what are called compensating mistakes. A group will make two different mistakes that happen to cancel out, and they end up accidentally getting the right answer for the wrong reason. We have to call this theta from the positive x-axis here. And we're going to end up having a cosine here in a minute. Okay, so what we know right now is that the electric field from that little bit of charge that lives right there in magnitude is approximately K times Q delta theta over pi r squared. So I took this and I plugged it right there. Okay. Now, we're going to have to do an integral. You can never integrate over a magnitude for these. You always have to integrate component-wise. So I have to find my components here, my EY, I, and my EXI. So I have to break this electric field vector up into his components. Now we're going to make an argument here. Again, I'm basically doing most of this problem for you. We're going to make an argument that by symmetry, EY total, all the EYs cancel out. And we could see that. See, we've got this little chunk of charge up here, creates a vector that points down. I get this negative EY component. I've got a similar spot down here that would create an electric field vector that points up this way. That EY there will cancel out this EY here. So once we integrate over everything, the EYs are going to cancel. We could actually just do the integral. We could calculate EY, and you'll see you would get 0. Okay, now we got to figure out EX. So we're going to call this angle here alpha. So alpha is this angle below the x-axis here. So I'll draw that picture a little bigger. Here's magnitude of EI. Here's the y component of that. And here's the x component of that. And this is the angle alpha. Then cosine of alpha will be adjacent over hypotenuse, which means EXI, who we're actually going to end up calculating, is magnitude of EI times cosine of alpha. Okay, now notice the relationship between alpha and theta. I want you to notice here that theta was this angle here. Alpha plus theta make a right angle. So if we're in radians, alpha plus theta equals pi, or alpha is pi minus theta. Or if you think in degrees, alpha is 180 degrees minus theta. Why do we care about that? Because I have to do my integral in terms of theta. I can't have an alpha floating around when the guy I'm integrating has to be from the positive x-axis going counterclockwise. And I've already got a d theta, a delta theta floating around here. I need everything in terms of theta. And alpha and theta are not the same angle. They're supplementary angles. Why do we care about that? Because cosine of, say, angle A is the opposite of the cosine of the supplement of that. We're going to pick up this extra negative sign. And for years, I did this problem, like we would do it together in class. And I would always end up with, at the end of the day, I would end up with this weird negative that just appeared out of nowhere. I could never figure out where it came from. I kept getting the wrong answer. And we would just make the argument in class that we know EX has to be positive. We got a bunch of positive charge back here. We know that the electric field is going to point along the x-axis and it's going to be positive. So where's this negative coming from? Right there. Took me a while to find it. So cosine of this angle alpha we drew in our triangle is the opposite of cosine of theta. So now we can put that on together and say the EXI, the ith contribution to the electric field in the x direction, is K. Just putting all this together. So I need magnitude times cosine of alpha, but cosine of alpha is negative cosine theta. So I'll go ahead and put that negative in here. I get a Q delta theta over pi r squared. I'll put the delta theta at the end. And I've got this cosine of theta. So this here, without the cosine, was just magnitude of the full electric field vector. Then the x component of that is that times cosine. And we picked up this negative because of this stuff here. This is the guy we're integrating over. This is the angle in our triangle that we've actually drawn, and those two angles are supplements. Okay, then from there, it's just we build a Riemann sum, we turn that into an integral, and so forth. So then we would say something like EX total is approximately equal to the sum from I equals 1 to n, where we had broken that arc up into n equal segments. EXI. So the sum over those. Then we actually, like, again, I'm basically doing this problem for you. We take the limit as n goes to infinity, which is the same thing as the limit as delta theta goes to 0. And then this sum becomes an integral. So then we would have EX total actually equals, instead of approximately, an equal. And this sum becomes an integral. This delta theta will become a d theta. And we got to fill in, like, you just go ahead and write it. Again, I've kind of done the whole thing here. Now we just got to find our limits. Remember, we're integrating over theta, and theta is always measured from the positive x-axis if we're doing a cosine. So that will be pi over 2 to 3 pi over 2. Remember, you always have to be in radians. So you actually do this integral. You're integrating with respect to theta. So all of these guys are constants. They just come out. And you're going to get that answer. Okay. I think that should be enough help.